Okay, we've done fun announcements. Now we're starting class. And at the beginning of week 3, we're doing personal finance decisions. Typicality and bell curves will go by quickly. Mortgages and saving for retirement will take a while. And these are more complicated than health decisions. The health decisions were all kind of straightforward. There were different formulas. And if you wanted to find out this kind of thing, you would plug the numbers into that formula. There were formulas for heart rate, formulas for DCI, formulas for how to use percent yield, yield percent, things like that. There wasn't really ambiguity. So the next topic gets more complicated. Typicality, we're going to talk in a moment about English language ambiguity. Just what typical means is vague. And what kinds of math we have to deal with that vagueness, because we don't want the math to be vague. The bell curves is complicated because there are things that vocabulary that should be used only for bell curves that are used for other things also. So that's another kind of language issue. Mortgages are complicated because each mortgage situation is a little different. Different upfront costs and down payments and fees and things like that. So there's a general sort of plan to walk through, but it's not as clear-cut and simple as just plug in the numbers and find someone's DCI. And then lastly, savings for retirement is complicated because you have different formulas and you have to know when to use them. There's simple interest and compound interest, and some of annuity do. And not only do you have to know what numbers go into the formula, but you have to know this situation needs that formula, and this other situation needs the other formula. In this third situation, first I start with this formula, and then I switch and start using the other formula, and so on. So that's why these get a little more complicated. But as before, things are hard when they're new, and none of this will stay hard once you do enough practice that it's not new anymore. Okay, so we're going to start with typicality and wonder about these pattern blocks. So I have here a electric scale that's much more fine than the one we used when finding yield percents in class. And I have our big box of pattern blocks again. So if you are kinesthetic, feel free to come up and grab a handful of pattern blocks. And my question is, assuming that a green triangle weighs 1.5 grams, which it pretty much does, then here's a group of pattern blocks. Let's make this bigger. So how much does a typical weight of a block in that group mean? And there's no right answer to this question, because the word typical doesn't have a precise mathematical definition. So if it helps, go ahead and grab blocks from the tub and build that collection in front of you and see if you can figure out a convincing argument, at least for yourself, about what counts as typical in that situation. Your number might be 1.5 or 3 or 4.5 or something made up of green blocks, or your number might not be a multiple of 1.5. That's fine too. I'm going to pause for a moment. Anyone have ideas right off the bat? Trisha, right?
Yeah.
Yes.
So my idea is that I would throw away the biggest and smallest, and in the middle would be those the 3 gram middle rock blocks.
Okay, so if I'll hold it up. 2 green make a blue. So Trisha is saying that in her mind, these guys are just too small to be typical. They don't count. And this one is too big to be typical. So the ones that are left must be the typical ones, and they are 2, so it makes a 3 gram total. Okay, that is a good defensible line of reasoning. Anyone else have something to say? Edwin?
So I've done them up in triangles. There's 17 triangles. The red makes 3 of them, the purple makes 2. And so I took 17 and divided by the number of pieces, which is 9, and came up with 2.83. That's 17 times 17 by 1.5, sorry.
Okay, so 1.5 times 17. And then, okay. So if you were to convert everything into triangles, there'd be 17 of them. You could pile them on my little scale if you really wanted to. It would come out to some number and then divided by 9 to get that.
Okay, because what it's saying is that one triangle is 1.5 grams.
Yeah. That's another perfectly valid way to say what is typical. Anyone have a third line of reasoning?
And you could say that the 1.5 grams is typical because it's in every single of those blocks.
That one's not as convincing to me because
has 1.5 grams at least.
Yeah, but they have 1 gram at least also. So not sure you sold me on that one as well. Okay, I'm going to move on. So, whoops, I need to go back over here. Okay, is this big enough to read in the back? So, some people focus on what appears most often. And this argument I actually didn't hear from you. That they say the blue block appears most. We have 6 of those, right? So they must be what's typical. That means 3 grams because the blue block is 3 grams. Other people focus on what's most representative. That's Trish's first argument. That the tiny one and the huge one were not representative of the whole collection. So we'll toss them out. And then we'll look at what is not tossed out, the ones we consider representative, and kind of revisit that question. Just among those, is there something that's most typical? And in this case, they were all the same, so that was an easy step. Some people want to do this average. They add up all the values and divide by how many there are. That was Edwin's answer. Oh, okay. Let's repeat the question. Now someone put 2 giant yellow blocks in just to try and get us arguing with each other. You can see Edwin is counting with his fingertip. He is not changing his plan. He's going to do the same thing with new numbers. Someone who hasn't shared yet want to say what their thinking is? You're lost?
Yeah.
There's no right answer to this. This is the kind of open discussion that you were starting class saying you didn't like. Okay, Amanda?
So I just wrote on my paper, I have like the 2 blocks that weigh 1.5 each, 6 that weigh 3, 1 that weighs 1.5, and 2 that weighs 9. And I did what you did last time. I added them and then divided them by 9. Yes. And I got 3.9
there's 11 things now, not 9, because we've added 2. Yeah. What was the total weight?
Total weight was 43.
So what did we get with 43 divided by 3?
I got 4 grams.
You got
Approximately.
that's 3.9. And how did you do that?
I did the same, but what I did was I did 1.5 times 29 and came up with 43.5 grams.
Ah, okay.
And divided that by 11.
So Micha had a little bit more here.
Yeah.
Okay, good. Okay.
You could also use percentages and just say it's 54% most typical, or most common is the 3. So go with 3 because it's 54%. The purples.
So more than half are the bluey purples. So okay, Tricia.
Just line them up and take one off your percentages in the middle.
Okay, so she's going to discard the smallest, discard the biggest, discard the smallest, discard the biggest, discard the smallest, discard the biggest, and then you have left of those. Okay, so this goes back to exactly the same things we said before. You could say, what's that? Can I click my box? Maybe I was smart and put all these in the box. Oh, I was. Okay. So what's most often? That's still the blue box. Blue diamond, more of those. Or you could say what's representative? That was what Tricia just ended us with. Toss out the extremes until everything looks more or less the same. Or you could do the total average. The 43.5 was correct. And then divide by 11. So all of those are great. And that's not what we want. We don't want 3 good answers to a problem. This is math. We want there, at least with these sorts of small problems, to be a right answer. So we need to do something. There's another lesson other than just that we need to do something. So that famous saying, there's 3 kinds of lies: lies, damn lies, and statistics. It's not necessarily that statistics are useful for liars, although in some cases that can be true. It's easy to massage the numbers if you know about statistics and make things have the answers you want. It's just that in real life, when situations have ambiguity, then you're going to necessarily have some disagreement about things. Statistics isn't some magic wand that removes ambiguity from real life situations. So one reason that statistics is a source of lies is that it appears that we've now removed the ambiguity, but it doesn't. You can't just throw math at something to make the situation clearer than it really is. Okay, but we want something that's not ambiguous. And so we need new definitions. The first one, you already know, it might just be a change of name. When you add up all the numbers and divide by how many, then the official name for that is the mean. It's not a great name. You would think if you're trying to avoid saying average, you wouldn't pick another very common English word, but that's what we're stuck with. So the mean is the kind of average where you add them up and divide by how many. Yes?
I used to say that the average person is mean to help remember it, even though that's not true.
True. Okay.
But it's a good catchphrase.
So, in many situations, the mean does what we want. It looks at a bunch of numbers. It provides an answer that's what's close to happening most often, and it's close to what's most representative of all those numbers. So here are a bunch of preschoolers. One of them weighs 34 pounds. 3 of them weigh 36, 2 weigh 37, 1 weighs 38, 2 weigh 39, 2 weigh 40, 1 weighs 41. And we could ask, what's the mean weight of the 12 students in the room? What's the average weight? In real life, when somebody says average and doesn't tell you what kind of math to do, you should always assume it's the mean. Add them up and divide by how many. Some people are typing on their calculators already. What's the total?
34.75.
34.3 is what I got.
Let's start with the total. When you add up all the numbers,
453, but I'm probably wrong.
I'll cheat and go look at my little thing here. It is 453. And there's 12 preschoolers, so we get about 38 pounds. So this should be old things you've learned a long time ago. Add them up, divide by how many. The official name is. Okay, more talking. If there's a balance scale, the mean is where it balances. So if we have 2 2s, a 6, and a 10, does it really balance? If we put it on 5, so 2 and 2 is 4, and 6 makes 10, so 20. 20 divided by 4 things is 5. Yeah, it balances at 5.
Wait, what? I'm confused. That so is the 2 representative of the weight?
Yeah, or the spot in the scale in this case. Each block weighs the same, but these are pushing it on this side, these are pushing it on that side. And when I add them up, and then divide by how many, even if they were weights or something, let's go to the previous slide, then our average weight was 38. 38, so we're saying that it balances there if that's a teeter-totter. Our eyes are remarkably good at this. Almost everyone, if you give them a histogram and say, where is it going to balance, they're going to agree on pretty much where the balance point is. Okay, let's keep going. So we just used that thing called a histogram. Let's define that carefully. A histogram is a bar chart. Each bar counts a different category of things. So that means that the x-axis, the bottom axis, has to be categories. In this case, how many pounds a preschooler weighs. And the y-axis, the left side axis, has to be accounting. How many have this? You can have histograms of all kinds of things, because you can count lots of stuff. Here is one, let's make it a little bigger, from some old Math 25 scores.
What's the definition of?
The definition
I got the bar chart, each bar
counts a different category of things. Sometimes the categories are numeric values, like weights or grades, and then you would want to write them in order. Other times, they're not something with any natural sorting. Different countries, and how many people live in each country, or have a certain disease in each country, or are educated in each country, or cities, or foods, or something. So sometimes what's listed on the bottom doesn't have any natural order, and that's fine. Okay, in this histogram, what I want you to notice is that each student has a piece of bar somewhere. If I was to say 3 students got either 86 or 87, that's what this bar is about, then that means that here's a student, and here's a student, and if I get another color, here's a student, right? So maybe this one is Maria or something like that. There was a real person that got a real score here. And each little section of bar represents one sample from the data. Okay, oops, what else do I want to talk about? How did that get big? Oh, because it went there. So because each part of the bar is one test, right, one student score, then you could actually start counting sections of it. So you could say how many students scored between the 80 and 90, 1, 2, 5, 6, 7, 8, 9, 10. You could say how many students took the midterm. I could count all of the bits of bar. So, everyone okay so far with that? So histograms are designed. The histogram above each category is 1.7%, starting at 48. So it starts here at 48, and it's not quite 2%. It's 1.7. By making each category, and the official name in math jargon is bin. Imagine you're like sorting socks into bins or something, cleaning up your kids' playroom. If each bin is 1.7, that made the clumps look nice. You could really see, here's an A clump, here's a B clump, here's the C clump, here's the D clump, like that. Yes.
Are the numbers on the side of students called bins too?
No, because they're counting how many things are in each bin. So if we change it, make each bin 5%, this is exactly the same data. You would count the same number of students. You could find Maria where her test score is. But now it doesn't look so clearly like there's A, B, C clumps. So this is part of lying with statistics. If you have a data set and you're making a histogram, your choice about how wide each bin would be, if it's numeric data, is going to change the shape of the histogram. And maybe that's a choice you make on purpose because you want it shaped a certain way. Or maybe you're just oblivious and you're not even realizing that you're making it shaped a certain way. So be a little cautious of histograms. Sure. So that one, the bins are smaller. Fewer students fall in each bin. It spreads them out more. This one, the bins are more than twice as big. More students are collected in each bin. And that looks very different. Okay, there's some problems I'm going to skip over here. So there's the word bin. One last bit of vocabulary about the mean is that we want the mean to describe what's typical of the group. And we need a word to describe how well it happens. So that word is down here, the standard deviation. And deviant here just means distance. How much it deviates from what's the mean, from the average. It's not deviant like unpleasant in some way. And so it's measuring how much things deviate. So the bigger your deviation, the more poorly the mean is representing the group. If there was no deviation at all the numbers would be exactly the same. You just have a spike for your histogram. So let's go back to these.
So the different levels is called the deviation.
Yeah. The number you could calculate, we're never going to, is the standard deviation. There's other types that are almost never used. So the formula is just too complicated for us, and we don't care. What we do care about is that that name is there, and we can kind of eyeball this. So which of these four has the lowest standard deviation? Things are most clumped in the middle. C is the most clumped. More things are in the middle. The average is going to represent more things in this group. Very few are too big or too small. Which one is next for standard deviation? D, yeah. Now what's average is a lot less representative. There's more things that are over here or over here on high or low edges. But there's still some things that it does represent well. And if we were to pick a different thing and call it average, that would be worse because there'd be some that are really far away. So picking the middle would still make sense. Okay, what's the next highest in increasing standard deviation? Not the worst representation, but second to worst. Why is it A and not B?
Oh, because there's two groups. No.
The groups are closer together in A and B, they're at the opposite ends.
Yeah, so this big clump and this big clump, there's nothing that's right at the mean anymore. That's an empty spot. But these aren't too far from it. It doesn't really make sense to say what's average when there's two distinct clumps. But if you're forced to try and pick something as average, this would still be the best thing because the other stuff isn't that far away and it's balanced. This one has the highest standard deviation. It's like this data is allergic to the middle. And it's rushing off to the edges to get far away. So if you're trying to do some research or reading about some research because you're shopping for whatever, medications for your grandparents or something, then if the data has a high standard deviation, that means that you can't trust it. There's nothing typical in that group of data. If it has a low standard deviation, that means that your statistics are more reliable. Most things are happening like the average would say. So that's what you get out of this. You don't actually have to put numbers to the standard deviation.
On the news or whatnot, when we come across statistics, if they offer that, what standard of deviation is acceptable?
It depends on what you're measuring.
Okay.
And usually you won't ever see it as a number, except in technical papers on PubMed or whatever. What you'll see is error bars on your graphs.
Oh, okay.
And that's saying how accurate we think these numbers are. Each spot on our graph is actually an average of lots of data, and how big is the deviation around it. Okay. If you ever wanted to, you could just go to an online website, put in the numbers, and hit calculate. You don't need to know the formula, but you will probably never need to do that. Okay. All of those four histograms we just saw were mostly symmetric. They all had something in the middle that we could call the average, even if it wasn't very representative because the standard deviation was high. But what if the group of numbers isn't symmetric? There's something that's just way high or way low. So we're going to go back to our preschoolers. Here is their weights again. And 3 of them have stuffed animals that weigh either 1 pound or 2 pounds. So they insist that their friends are included when we find the average weight for people in the classroom. So what would the new histogram be like? And what is the new mean for the weights of all of these 15 friends?
And the mean is, I think I'm still kind of.
Okay, the mean is add them up and divide by how many?
Then what's the median?
The median we'll get to in a moment. I can show you right now if it helps ease your mind. No? Okay. So let's actually do this. Get out a piece of scratch paper by yourself or with somebody around you. Sketch. Don't be a perfectionist with art. Just sketch real quick a sloppy histogram with 1, 1, 2, 34, 3 36s, 2 37s, a 38, a 39, another 39, 40, and another 40. See if you're eyeballing it. Gives you a correct balance point. Actually add things up and divide by how many to double check.
Here. So wait, we're not going to put the number between, so we have to like 1 pound, 2 pound, 3 pound, 4 pound, all the way up to 40.
No. Well, I guess I don't know.
Okay, who can answer Amanda's questions? Do you need the bottom of your histogram to start at 1 and go all the way up to 41? Yeah.
Yeah. Okay.
Otherwise, you're not going to have a place for some of the bars.
That's going to change the shape.
Why does it say 1, comma, 1, comma?
Because there's 3 stuffed animals.
Got it.
Okay. so I will try this also. Am I going to have room to do that 4 times? No, I'm not. Okay. Whoops, I forgot 35. Okay. You can come up and show me yours on here if you want. I made a choice just because of the screen I had to work with to make each bin have 2 numbers. This is 1 and 2. This is 3 and 4. This is 5 and 6. This is 7 and 8, and so on. So my histogram will be shaped differently than yours if you did every number separately. Just eyeballing this, where does it look like the balance point would be?
23, 25.
Somewhere over here.
Yeah, maybe 27.
Did anyone do the math yet to actually find the total? And then so 457 divided by 15 is 30. So the actual balance point, the actual mean is going to be 30. Does that look reasonable to our eyes?
Really, if you're describing, nutritional facts for children and averaging it out, you don't want to hit a 30-pound child because you hit none of them.
Right. Well, that is true. This mean is not representative of anyone in the group. Right? The actual children weigh more. The stuffed animals weigh much less. So this is one of those cases where the mean is not doing its job. It's not most common. It's not most typical. It's not most representative. Whatever English word we want, it's failing. Okay. So, but in real life, you have this happen all the time, actually. It's not with stuffed animals, but with other things. So, Tricia did an amazing thing back earlier. She said, let's take the smallest and the biggest of the shapes and toss them out and repeat that until we get to something in the middle. Remember when she said that? So that's what the median is. We need a different kind of average. We're going to list the numbers in order. This is important because there will be somebody that forgets, certainly on the homework, maybe on the test, to put their numbers in order. Put your numbers in order. Then pick the middle number in that sorted list. You're throwing out the edge ones pair by pair until you get to them. Now, if the list has an odd number of items, there will be one that's the middle item in the list. So that will be your median. If your list is even, then when you discard, starting at the edges and working towards the middle, there's going to be 2 left. Does that make sense? If we had 6 things, then we can throw out those, and we can throw out these, and then there's going to be 2 left. So there's no middle item. What do? We're actually going to take the mean of those 2, add them up, and divide by 2. That's the best we can do to say the middle item of the list, is we're going to make a fake list item in between.
So the answer would be 1.
So if we say, what's the median weight of all the friends in the classroom, I'm going to sort the list. Again, I'm going to peek because I don't want to have to list out everything. We'll cross out the values. Get rid of that, get rid of that, get rid of that. And then average those, take the mean of that, add them together, divide by 2, we get 36.5. Now if we go back to our histogram, we're at 36.5, which on mine is right here. So that's actually representative of the kids. What happened? Why does that number work better?
It uses real examples, real people. It's not just statistics. You're guaranteed to hit somebody.
You're going to actually hit something there. What messed up the 30, the mean? The little ones, right? The stuffed animals. Why didn't the stuffed animals mess up this one?
Because they weren't fed.
Yeah, we just tossed them out. So that's what the median is. In real life, you probably don't want to cancel things out one at a time. Be a little more efficient, and after you get your sorted list, say, oh, I'm going to cross out like 5. Was that enough? Nope, let's cross out another. Okay, there we go. That's easier. So this happens all the time. It focuses on what's most representative. It can also do a respectable job at most common. When do you use this? For things like company salaries. You don't want to count the CEO when you're saying what's the average company salary. You should use the median. Otherwise, it's going to be like the stuffed animals in the other direction. Or state incomes. Neighborhood house values. Just because, I don't know, somehow I inherit a lot of money and turn my house into a mansion doesn't mean my neighbor's house value suddenly goes up that much. In other situations, the lowest and highest ones aren't representative, so we'll just throw them out. Focus what's on the middle of the list. Okay, don't listen to this. Just for the sake of completeness, there's a third type of average called the mode. They're always taught together. You'll see things online or in older books, the mean, the median, and the mode. We never use the mode, so don't worry about this. The mode is just which is the thing that appears most often in the list. So this is great for voting, who's the class president. But in most life, when you're talking about average, you're not thinking about which one are there 4 of instead of 1 or 2. So the mode isn't really useful. Okay, there's a factfulness thing you can read at home about generalizations, not assuming things are more typical than they are. And success, we can do that. Okay. We're going to stop, not talk more about bell curves, save that for tomorrow, and spend the rest of our time doing the homework comparisons. So you can now do all the typicality homework if you wanted to rush ahead. but we'll talk more about it, do more examples on Thursday. If you want to wait, that's great too. I'm going to turn off the recording but keep my screen capture going for if people have homework questions that want me to write.